Yeah. So from the ICID, welcome to the webinar on updates and advances in the FAO56 crop water requirement methods. As we all know, the crop evapotranspiration and the water requirement of crops form a very major component of the water management scenario in any basin. And FAO56 has been a bedrock of planning as well as designing and also at times estimating the water requirement for the crops at the field level and also even at the large projects level. So this webinar is a landmark in the sense that we are now going to discuss the basis and the updates and advances that are required and that can be made in the existing FAO56 guidelines, so that the guidelines become more appropriate for the current scenario, and those scenarios which have hitherto not been looked at, they can also be brought in respect of the crop evapotranspiration. So we have a very eminent panel of speakers moderated by our president, Professor Dr. Ragab Ragab. And then we have Dr. Luis S. Pereira, Vice President Honorary from University of Lisbon, Dr. R.G. Allen from U.S. Department of Agriculture, Dr. Paula Paredes from University of Lisbon, Dr. Ramón-López-Urrea, Institute of Agronomy, Provincial Agronomy and Water Management Research, Dr. Nebo Jovanovic, University of Western Cape Town. So we have a very eminent panel of speakers, and they will be introduced as and when our moderator, President Ragab, will introduce them. Next, please. Yeah, these are the presentations that we will be making. That is the updated approaches on standard and actual KC and basal KCB and their estimation, importance of weather station, siting, the approaches to cope with the reduced data sets, and then the use of lysimeters and EC systems for the measurements, and then Dr. Nebo finally will provide the impacts, advantages, and issues when adopting the updated approaches to FAO56. At this stage, I would request to mute all participants to mute themselves and then take up the discussions later on. The questions and answers after the presentations, we'll be having the question and answer sessions, and you can keep on sending your questions, which should be as far as possible short and specific. After the written questions, if the time permits, the participants may be requested to share their experiences, and then please indicate your willingness to share your experiences by raising the e-hand. So wishing you all the best for the webinar, and I welcome you once again from the ICID and also these eminent academic institutions to this very important seminar on FAO56 updation. Thank you very much, and I would now request Professor Dr. Ragab Ragab to please take over the seminar and conduct the seminar, please.
Thank you very much, Secretary General. I would like to welcome you all and have a good day wherever you are. At the same time, really, I would like to welcome our distinguished professors and excellent speakers of today for such an important, really, issue. And let me just get into a small introduction and about FAO56 Irrigation Drainage Paper 1998, which was a joint work between FAO and ICID. The working group on efficient use of natural resources in the 1990s carried out this work through the significant contribution of Professor Richard Allen, member of the working group, and Professor Luis Pereira, who was the chair.
Make your full screen.
Sorry?
Make a full screen slideshow.
Okay. Is that better? Yeah. Is that okay? Hello?
Yeah, it is.
Yes, it's okay.
Okay.
It's
So
okay.
the FAO56 really was a joint work between FAO and ICID, and the working group that actually produced that FAO 56 was the efficient use of natural resources, and that was really under the chairmanship of Professor Luis Pereira, Professor Richard Allen, and myself, who were members of that group. Then I had the honor and the pleasure to be a member of working under Professor Luis Pereira, and then I became the vice chairman and later the chairman of this working group. This working group has been moving with time to address pressing issues. Now its name is the Working Group on Water, Food, Energy Nexus. And the crop water requirements, as all we know, we estimated by different ways. One is the equations, and second is measurements by soil measurements, plant measurements, lysimeters, and direct measurements using class A pan, bound ratio, elecovariance, scintillometers, remote sensing, and so many things. Before the FAO56 came to light, we have been battling with a number of equations, type of equations based on radiation or energy, some other equations based on temperature, and some other equations based on the combination of two. And that's really was the case before the FAO56 came to light. And then we found the Penman-Montes equation in 1965, which actually is the first equation that introduced the plant presence in the equation of ET or evapotranspiration. However, because of that plant parameters was related to resistance, there were some difficulties in getting that parameter, and that actually limited or confined its use to the academics and the researchers. Then the FAO56 simplified the Penman-Montes equation and maintained the presence of the plant in the equation. And this is a simplified equation that actually took over from the other equations and appeared into the 56 FAO irrigation drainage paper, as you know. The simplification of this equation using representative seasonal average value of plant resistance made it easier to every irrigation practitioner to use. And this equation became dominant and widely used worldwide. The modified equation has unified most of us as irrigation practitioners who, prior to the modified Penman-Montes equation, used various equations. The number of citations of the modified Penman-Montes indicated the dominance and widespread use of the modified Penman-Montes equation and the significant reduction in the use of our old temperature, radiation, and empirically based equations. So science and technology have evolved during the 24 years since FAO56 was published, and a number of novelties have furthered the progress on evolving irrigation practices and management. Updates and advances can bring more accuracy into the calculations of crop water requirements, providing better support to precision agriculture and improving our responses to climate change. Updates and advances to FAO methodology and application that have been presented and discussed in the special publication 2021 issue of agricultural water management are quite relevant to modernizing management in irrigation, in irrigated agriculture, and to increasing water saving. So we have excellent, really, speakers, distinguished professors and researchers here today, and we are lucky really to have them among us today, and we'll be really very happy to listen to the updates. And I would like to you also to join me in thanking them for making themselves available to us today. So the presentation, as mentioned by Secretary General, will be by Professor Luis Pereira, Rick Allen, and then Paula Paredes, and Ramón López-Urrea, and Nebo Jovanovic. And I would like to introduce first speaker, our distinguished professor, Professor Luis Pereira. He is a professor emeritus in Institute of Agronomy, University of Lisbon, invited Professor Shyam Bari, Italy, University of Porto, and the University of Azores, Portugal. He is a research advisor at universities in China, Brazil, Dr. Honorary Causa, University of Rostock, Bulgaria, Honorary President of CIGR, and Vice President Honorary of the ICID, recipient of numerous awards conferred by ICID, CIGR, European Water Resources Association, and the various national and foreign institutions from Bulgaria, China, Egypt, Ecuador, India, Italy, Japan, Libya, Mexico, and USA. He's also a consultant to FAO, UNDP, and UNESCO, and he is benchmark contributors to the crop Evapotranspiration and co-author of FAO56 crop Evapotranspiration. He will today give us a presentation on the updated approaches on standard and actual KC and the basal KCB and their estimation from the fraction of crop cover, FC, and height. We all would like to welcome Professor Luis Santos Pereira. Thank you very much, Professor Luis.
Okay, thank you.
I need to.
You need to cut. Why?
Thank you.
We need to change. Okay, okay, okay. So I am very much pleased to share our work from developed after some time.
Professor Pereira, please make it full screen. Yeah.
Okay.
Yeah.
That's okay?
Yeah, that's fine. Thank you.
Yes, that's
Okay,
fine.
thank you. So when it was about 20 years past after the publication of FAO56, it was in 98, we decided to look for the advances that the research people all over the world had provided. And we updated several aspects of the FAO56. Nevertheless, one thing it was evident, it was that the FAO56 was effectively a benchmark. And it is such a benchmark that it has over than 35,000 quotations. And this is for a water book is extremely good. For operating, we used many authors and a few of them as editors. That is the case of Paula, Dr. Unsakier, Dr. Ramón López-Urrea present here too, and Dr. Nebo Jovanovic, that was in charge in terms of the agricultural water management. This can be looked through this link. And in my presentation, I just want to share all this. And sharing means that I am very pleased to have a non-visible audience, but that is not a virtual audience, but that is a real audience. And I am very pleased to share these with you. So, good morning, good afternoon, whatever, good to you. In this presentation, I will start, of course, looking for the main concepts, because the main concepts have been changed with FAO56, but there is not a real adherence by the research people. And these concepts are extremely important in the developments that we require in the day-to-day application of the methodologies. The first is that we converted Perman-Montis equation with the resistance surface and aerodynamic resistances for the flow of heat and water vapor into a simple, let's say simple, equation based just on climate variables. So it is not a modification, but it is just an application of the Perman-Montis for a grass cover. And so it is this grass cover responds to a minimum characteristics that it has to be well weighted and full covering the soil. This is a condition that is not always respected. And the aridity of the place changes the possibility to obtain the right or correct value for the reference gas evapotranspiration. When we have the reference gas evapotranspiration, ATO, we have a transfer coefficient between the crop that we want to study and the crop that is the reference, the grass, in terms of the difference of the evapotranspiration process. Then this Kc factor is a standard one when this crop is well weighted. When it is not well weighted, or when the crop is suffering some kind of stress, namely the saline stress, we have an actual case. This distinction between standard and actual Kc that has been on the base of the FAO56 keeps not adopted by many researchers. And of course, the consequence is that we don't know exactly what they are writing when publishing, or what they are writing, or what they are calculating when they are using these in the practice. In fact, if we just use the weather parameters, we just get the reference evapotranspiration. But if we just consider the crop, the pristine, well-weighted crop characteristics, then we have a potential crop evapotranspiration. We don't use the term potential evapotranspiration to do not mix with the old one before Montis did his development. Finally, you see, if we consider also the management and environmental factors that change the typical crop characteristics, then we have actual evapotranspiration of the crop. So this means that we need at least after 20 and 3 years or 20, now near 24 years, to make this distinction in order to provide the appropriate accuracy in calculations. We have not modified the Montes equation. We just have parameterized that Montes equation when the crop is grass. And that parameterization of the Montes equation resulted in our FAO56 ETO equation. We used to call it FAO56 PM ETO or just PM ETO, but the confusion that it is coming out from the many papers that I am reading after years, I prefer, and I am proposing this now, that we don't use the term PM for the FAO56 ETO. This equation of ETO would not have been possible without using the Montes equation for the grass reference crop. And therefore, the question is that there are several, not much, but there are several papers trying to propose a different approach by using a Lysimeter. But a Lysimeter, we know that there are problems with Lysimeters. Rick says that around the world, maybe 5% of the Lysimeters used are accurate enough for him to believe on the results. So we never used a Lysimeter with this purpose. We just used the conceptual approach of the Montes to get the grass reference crop transformed into an equation. If effectively, a big question that we have in the computations is that we need to have a green grass cover to get appropriate measures of the temperature and humidity that are basic for the energy balance that is included in the FAO equation. And nevertheless, there are stations like this one that is absolutely arid, and of course, it will not provide an adequate estimation of ETO for using in irrigation, because this is just for arid conditions. So an ETO that is informed by something like very strong advective conditions in addition to the local. Of course, not always it is possible to have a nice place, a nice station, but like in this example, in a mountain study, we may have something similar. This is not standard, but it approaches very much a standard condition. This question is dealt with care by Ricard and team in two papers into the special issue that allows us to convert the results of the grids that are provided through local information or through reanalysis in order to avoid the effects of aridity of the station. We, changing the subject and going to the crop coefficients, we of course studied the standard and studied the single and basal crop coefficients. And we studied these for vegetable crops, for field crops, for tree and vine crops. The concept is very easy and very simple, and a simplification that is refused, of course, by many of the researchers, because nothing is linear in the nature. But our capabilities to compute with curvilinear that changes from one year to the other, it makes the possibility to compute a KC almost impossible. This easy approach of using a KC that is represented by these segmented lines, you have the KCB, so that corresponds just to the crop, and the K and the KC that is adding, that is this third line, where the difference between these two lines is the average contribution from the soil, from the soil evaporation. This concept is very easy to transfer from one place to another place. And of course, the detail, or if you want, also the accuracy is better when we use the KC represented by the daily KCB, or daily transpiration coefficient, added by the evaporation coefficient. If there is stress, the stress affects only the crop, not the soil evaporation. And the stress coefficient applies only to the KCB. This idea is effectively followed by the common colleagues. The question is that we don't have a very nice follow-up in terms of the recommendations that are behind this segmented curve. Because in this segmented curve, we just need 3 values. When you have a curve, you need many values. So in research, many values is okay. In the practice of the field, 3 values is about the maximum. And the 3 values are always the initial, where soil evaporation is the important factor. Then we have the mid-season, when the crop is about fully developed until maturation. And the third is at the end, at the maturation or at the harvesting. But the people tends to use an average value between the end and the mid. I don't know why, but it is of course more easy to compute, but it will cause a bit more requirement of water for irrigation. Another thing that is forgotten many times is that the transferability of KC and KCB requires adjustment to the climate. That adjustment to the climate was a very good innovation proposed with the FAO56. And we assume that the standard climate, because if we adjust, we have to have a standard climate, and this standard climate is with the relative humidity minimum. Relative humidity is 45%, and the minimum, the mid wind speed at 2 meters is 2 meters per second. For developing or updating the coefficients, we and others, we followed 1,330 papers, but we rejected most of them because something was impeding to get the appropriate transferability. And this selection for the potential transferability is naturally extremely important. I suppose, after my long experience, is that if we publish, is to not to be recognized as somebody that publishes, but it is to transfer some ideas, some values, some methods to the colleagues that are in other places, including in many times in other climates, in other conditions, in other practices, and share the research results. I hope that this idea of the transferability causing publication would be more relevant than just publishing to be recognized. Main problems that we found for the transferability that caused that we abandoned nearly 850 papers is that many people did not use the GRASS FAO ETO or the ASCE ETO, but other equations, or not use the standard segmented KC curve that could that is the typical approach for the transferability, but or they not use the KCN, but just a value during the late phase, and we don't know which is the KCN, or they use a time-dependent KC that is not transferable at all. That is the monthly means, but the month is the month's value is that the month's value that was observed in that particular year where research was done, or equations that just make the KC depending on time. Many papers do not produce sufficient information on field and computing methods used. So they could not provide enough information to certify the accuracy of the potentiality. Excuse me, I don't understand. Others use only one crop cycle, and one crop cycle may be special without showing others, or models used are not calibrated, or they don't consider the availability of energy, and with several KC values larger than 1.3.335 show up like already this year, 2022, there are published KCs that approach the value 1.9. That is impossible. Even with advection, there are some errors somewhere. So we distinguishing this problem of the pristine crop from a stressed crop is evident here in these pictures, where you can see that there is no there is no KCB values that come out of the segmented curve, while here they are, these red ones are the values below. And of course, the crop has to produce a KCB actual that is reduced relative to the KCB standard. We looked for the same crops that were in the FAO56, and we added several ones. The fact it is, in particular, we add the herbs, spices, and some special crops into the vegetable crops. In the field crops, we added, for instance, the black and green gram that is very typical from India, and we add some others that are becoming more popular, like quinoa and teff. The information provided to the readers tells for each crop which are the references that produce the information, where this study was developed, how it was studied, and which irrigation method was used. And we get we place the values that are produced by the researcher, as well as the values that result from adjusting to the climate, the values effectively produced by the users. We also added some values that are important for the producing the soil water balance with the crop, and we consider that this is extremely important, not to follow what we are repeating here in the publication, but that things are observed, at least when more accuracy is required. For rice, everything changed, because rice nowadays is not resuming anymore to the flooded paddies. The flooded can be with dry seeding or with anticipating cutoff. Modernly, there are intermittent application of water, and so there is not a large value, a large fluid, and there are also aerobic irrigation by sprinkler or by basin irrigation. So the approach that is provided in FAO56 is in fact an advance relative to is not so advanced as that we produced in our papers. When we reproduce or propose the updated values, we show these updated values comparing with those that are in literature, with those that were proposed in FAO56, and we can see that there are some differences. In these applications, for instance, there are the cases include some values that are about the same, and some values that are smaller, and some values that are larger. I don't know what is absolutely truth, but this is an indication, and normally a good researcher knows to judge the values that we propose. For vines and orchards, we have been including a little bit more trees and fruit trees from our temperate climates, but especially we included also several tropical and subtropical crops. So this is an advance, but the best advance with this approach is that we consider the plant density, for instance, as you may see, so the plant and the training system. If there is an overhead release, an horizontal release, a teeth release, or a Y-shaped release. And we compare the values that we go to obtain with those that result from literature, with the previous tabulated in FAO56 or by Allen and myself in 2009. And we got just a new approach that is not a single value or two single values, but several values on KC mid and KCB mid or KCN and KCB end. Of course, the simplification still is large, but we approach a little bit the conditions. That study with Allen, that was a very nice one, on estimating crop coefficients from the fraction of ground cover and height, was developed during the last 12 years or 10 years, let's say, and we verified in the first publication that it works well, and we predicted the crop coefficients, and we produced the information required for these aspects, in particularly focusing the parameterization. We have to note that these values are the actual values that are observed in the field. These are not the standard values. These are actual values. This is for supporting irrigation, water management, resource conservation, whatever, but not to be considered, of course, to be considered as a standard value. I just move fast here. So we develop a density coefficient, and we have to use some kind of new parameters. The curiosity for that, these parameters are difficult to obtain. No, some are observed very easily. That is the height of the crop and the fraction of ground cover. Others are less easy. The MEL is a parameter that refers to the porosity of the canopy relative to the solar energy. The FR is the adjustment that the crop that the crop introduces itself to respond to the possible stress. These values, using these values, we obtain KCB and KE that are effectively similar to the standard but it is similar to the standard because we use the standard values for FC and H, as well as for FF. For the vegetable crops, we also applied these. And this is in the various countries that have published results using HFC, MEL, and FR. And you can see that these are with a nice coefficient of regression and with a nice coefficient of determination. These are two of them, but others are similar. For the tabulated values of KCB for vineyards, from various colleagues, namely Dr. López-Urrea here present, the regression coefficient and the determination coefficient are also nice. For the field crops, things are also quite nice, but they deviate a little bit from the objective R-square. We had occasion to work with the Forrest Melton from California that is using a model, the model CMIS for remote sensing, and the results from the remote sensing ET and from the energy balance ET, the remote sensing using this application, this application developed by Alan and myself, shows that we have a quite a nice regression coefficient and determination coefficient. Okay, this is similar with the observations that we performed in Portugal, and the application for in this case for vegetables and field crops is also quite nice. The R-square can never be equal to 1 because we mix here several crops and dates. This application for cereals and oil crops and vegetable crops is good. I thank you very much, and I excuse myself if I took a little bit longer, but it is important to share what we feel it is good after several years working with the colleagues, like it is the case of working with Rick Allen that follows me in his presentation.
Okay, thank you very much, Professor Luis Pereira. And we will have a discussion after all speakers.
Yes.
Okay.
Yes.
So
Thank you
now
very much.
we can now stop sharing. Our next speaker, Professor Richard Allen, and he's a professor in water resources engineering, University of Idaho, and he has developed computerized tools to quantify crop water consumption over large areas using satellite imagery that received the Innovations in American Governance Award in 2010 from Harvard University. He is currently a member of NASA Eco-Stress Science Team. He is the first author of the United Nations Food and Agriculture Organization publication FAO56, Crop Evapotranspiration, that serves as international practice standard. Alan received Outstanding Faculty Award in College of Engineering in 2010. He has received the Arid Land Hydraulic Engineering Award and Joyce Tipton Award from American Society of Civil Engineers, and was the 2016 Irrigation Association Person of the Year. So without really any delay, the floor is yours, Professor Richard Allen. 15 minutes, please. Thank you.
Okay, thank you. I'm not sure if you can see my screen.
Not yet.
Okay, let me try sharing once more.
Good.
Yeah.
How about now?
Yeah, it's
Good.
excellent.
Okay, very good. Well, thank you, Dr. Ragab. It's a real pleasure and honor to speak on this topic and to speak to a global audience. We all appreciate the importance of evapotranspiration estimation. Today, I would like to talk about how we employ the estimation of ET to large areas. Generally, in water resources management, we need to have very good estimates of irrigation water requirements, both for management, for water rights, transfer and purchase in the US, or just regulation. And so many of our government agencies need the best estimates that they can on irrigation water requirements. I'd like to recognize my co-authors here on this publication. What I will be talking about primarily today, let's see, I'm having a difficulty getting my, okay, did that switch okay?
Yeah. Yeah.
A recent publication in the Transactions of ASABE gives a lot of the details, so I won't go into so many details. One of the applications where we use the FAO56 methodology was for a climate impact study in the Western United States in some of our major river basins shown here. All of those dots are weather stations that were employed, and I'll talk a little bit about specifics. And then we looked at the impacts of a warmer future, a drier future, a wetter future on irrigation water requirements. So we use the, and then in my home state of Idaho, which is in the northwest part of the US, we routinely provide updates to irrigation water requirements for well over 200 weather stations. Some of them are National Weather Service stations that only measure temperature and precipitation. Others are full featured stations like the US Bureau of Reclamation Agrimet station. Also, our model that I'll mention a little bit later has been employed in the state of Nevada also for the same purpose. So as Lewis touched upon, we're using the FAO56 and ASCE Pima-Monteith. For the Idaho applications, we use an alfalfa reference, the tall reference. But for the climate change study, we use the short reference, which is identical to the FAO56. So it was adapted and promoted by the ASCE, American Society of Civil Engineers. So we use the dual crop coefficient method that Lewis has explained. One of the challenges of applying this methodology, the dual KC methodology for estimating irrigation water requirements, is to estimate the evaporation component, especially as impacted by the irrigation. So we need to make an estimate of how often we will have irrigation and the associated evaporation with that. So in our applications, in our model, We use a soils database to give us an idea of the evaporatable water in the soil, estimates of management allowable depletion for each crop. Then we simulate irrigation events which vary from year to year according to the weather, according to precipitation, to give us that additional estimate of the KE. So this is just an example of what we produce. This is for spring wheat, the final KC, just over a 2-year period, so that we can see even the winter time. Where in Idaho, where this example is from, we have a snow cover at some of our sites. But we can see the individual estimates of KE either from precipitation events or from irrigation. In fact, here are the simulated irrigation events, these vertical lines. For winter wheat, and then we transform this into millimeters per day, and we can see that ET in a winter temperate climate like Idaho is quite small. Most of our evapotranspiration is during the summertime. We also, and for alfalfa, for example, we need to simulate cuttings. So we use a phenology clock for that I'll describe a little bit. Let's see. So Lewis talked about difficulty in estimating variable time in a crop coefficient method, but we really do need to do that when we are applying a method year after year after year, knowing that some years are cool, some years are hotter. So that affects the development of the crops. And also for climate change study, where we have an earlier planting date, maybe a shorter growing season because of the additional warmth, the crop develops more quickly. We expressed the weather effects as part of a growing degree day. And then we accumulated that. So every day we accumulate growing degree days. And then finally, we normalize it. That's what the N stands for here. We take the cumulative growing degree days on any day and divide by the cumulative growing degree days required to reach full cover. So that first beginning of the mid-season that we have on the FAO56 curve, we are attempting to estimate when that occurs. And then we normalize everything. So it goes from 0 to 1 during the initial period and development period. This is just an example of some crop coefficients measured by Lysimeter at Kimberly, Idaho by James Wright. And what I want to show here is the basis here is the cumulative growing degree day. And so because it's normalized, we have 1 when we estimate reaching full cover. And then beyond that, it's just a scaling of that full cover value. But what's remarkable is that so many different crops have very similar progressions in development after we normalize them. So that gives us some confidence that from year to year, this method can be fairly consistent. Another thing to point out is with the alfalfa reference that we used in Idaho, just because of tradition, the maximum KC is 1. And we see that for many, many crops. And as Lewis pointed out, with the methodology to estimate KC from fraction of cover, that's why it works fairly well. Most agricultural crops have been developed with a lot of stomates, and so they're very good converters of energy to vapor according to their leaf area fraction of cover. The only exception is potatoes, which have some more stomatal control, and so they have a lower maximum KC. To estimate the beginning of the planting season in a cold winter climate like Idaho or the Pacific Northwest of the US, we take a 30-day running average of air temperature. And as soon as we hit some value for any particular crop, we assume that that crop is planted or that green up occurs. And we use a 30-day because it dampens out, as shown here, individual daily fluctuations. We get a smooth curve that's monotonically increasing. And we use it as a surrogate for soil temperature on when farmers will plant their crop. We estimate the killing frost anytime we have a cold climate with frost. We have to establish some temperatures where we believe the crop will be finally killed by the coldness. So this just gives an example of using this growing degree day approach. This is the length of growing season for alfalfa hay as a function of elevation. Excuse me, this is in feet, my apologies, feet above mean sea level. And we can see that, of course, as we gain elevation, our air temperature is cooler. And so, and we have frost more early. And so we see the length of the growing season for a crop like alfalfa forage reduce with elevation. So this is one reason we use the cumulative growing degree approach and killing frost and such to terminate, because we do know that this is highly variable. Now, a flip side is if we look at dry beans, which is a discriminate crop, we see that as we gain elevation, we actually lengthen the growing season. And this is because the cooler temperatures reduce the development rate of the crop. And so it just takes more days to fully develop that crop and bring it to maturity. And field corn is shorter again because it's usually a longer season crop and it's going to get killed by frost generally, but that's not always true of some of our modern varieties. So just a little bit on estimating weather parameters where we only measure temperature and precipitation. One of the philosophies of FAO56 is that it's better to stay with the theoretically and physically correct Pima-Monteith equation and estimate the missing data rather than to retreat to a temperature only based method. And we feel that our best estimates of these parameters are better than no estimates as represented in a temperature-based equation. So we estimate solar radiation similar to exactly the same as FAO56 from max min daily air temperature. TDEW is related to minimum daily air temperature minus some offset that we vary with elevation and space. And then wind speed can come from long-term records. A little bit on snow, I think I'll skip that. We needed to develop coefficients for desert vegetation, not for irrigation, but for water balances such as groundwater flow models, hydrologic studies. Many of our users are quite interested in our natural systems. And of course, a reality check. If I apply this method to a rain-fed situation and estimate total ET, I hopefully do not have more ET than precipitation. So that's kind of what we call a reality check. And here's a plot of a number of years of annual evapotranspiration versus precipitation. And we can see because of some random error in the model uncertainty, we do exceed it by a small amount, but by and large, we agree with precipitation. And these years where ET is less than precipitation means that we probably have some potential recharge to groundwater. We have published our results on the internet so that anyone in our state can download time series of data or statistics, and that's been really well received, this very quick, easy access to data. Here's just a website. You can just Google for ET Idaho, we call it in Idaho. So in Nevada and the Western US states, we've used our original ET model. We now call it the ET demands model. You can Google for this. It's available on GitHub. It's an open source model. It's now, originally was in Visual Basic, but now it's in Python. And we have a lot of crops added for California where there are almost 100 different types of crops. Let me just skip past this. So just to finish on this climate change impacts. A lot of computations, but boiled down in this case for the Colorado River Basin. The various scenarios that were looked at were a warmer, drier climate, a warmer, wetter, hotter, drier, hotter, wetter, and then really a central tendency, which is kind of the average of all the global climate change prediction models. And it's really difficult to see these graphs, but we can see at the high elevations up in Wyoming, Colorado is where we saw the largest increase in irrigation water requirements. We saw the least amount of increase down by California, which is shown here near the mouth of the Colorado. And that makes good sense when we think about it, because it's already hot and dry with a 12-month growing season at the low elevations. But in the high elevations, we're going to see an extension of the growing season, and coupled with the hotter weather there, we'll see a more substantial increase in evapotranspiration. So I will quit there. And again, if you're very welcome to use the CT demands model. It's got all the FAO56 dual crop coefficient embedded in it. And it also has kind of a GIS sub-base for it to handle spatial information. So with that, I'll thank you.
Thank you very much, Professor Richard Allen. Thank you for sticking to the time as well. Thank you very much. And sorry to keep you awake all night.
Oh, my pleasure. It did rob me from my beauty sleep, but I'll recover.
Okay, thank you. You can stop sharing now your screen.
Okay. How's that?
Okay, that's fine. So now our next speaker is Dr. Paula Paredes, Assistant Professor at the School of Agriculture, University of Lisbon, Portugal, and research at LEAF, it's the Landscape, Environment, Agriculture, and Food, and ISA, University of Lisbon. Currently, she is Associated Editor of Agricultural Water Management Journal, and she is also a member of the editorial board of the International Journal of Environmental Research and Public Health since 2019, and she also a member of the editorial advisory board of the CABI journal CAB review since 2021. The floor is yours, Dr. Paula. Thank you for giving us this valuable chance to hear you and updates on FAO. Thank you.
Thank you very much, Dr. Ragab. I will share my presentation now. So, first of all, I want to thank the ICID for giving us the floor to expose the advances on FAO56. And today I'm going to speak about the problem that we face in many countries in the world, even the most advanced ones, that is the reduced data sets. Sometimes we have gaps in our weather data sets, and how can we do to cope with this reduced data set? So we have alternative ways to do so, and we are going to talk a little bit about it. So the first thing that I'm going to speak, it's about the integrity of those observed weather data sets. We need to first look at the quality of the observations prior to its use. Then I'm going to speak a little bit about the FAO56 Panama-Montes temperature approach. So coping with the gaps in the weather data sets, and the Argris-Samani equation for computing also reference evapotranspiration. And I'm going to speak about the reanalysis and other gridded weather data sets, and finally using satellite weather data and related AT products. So as already spoken, the FAO56 Panama-Montes equation requires weather data on temperature, dew point temperature or relative humidity, sunshine hours, number of sunshine hours or solar radiation, and wind speed measured 2 meters high. When we do so, we first have to look that this data is collected in reference sites. So downwind of a reference dense grass, fully transpired and clip grass. So first, we have to see if the data, the observed data, has errors of estimation, of observations, of measuring. So for instance, when we have shortwave radiation, we have to look to see and compare with the clear sky radiation, that is the maximum that could be observed. Especially, we can see it during the summer months. This is in the north. So during the summer months, this example, you can see that the shortwave radiation is much below the clear sky radiation. So we have to correct those observations in order that they approach the clear sky radiation conditions. So here is another example, and we can see pointing out the malfunction of the sensor. So again, we have to look for this kind of errors. When you look at the wind speed, it's very difficult to assess the quality of the measurements. So what we can do is to compare nearby stations. This is an example of the comparison between two weather stations measurements that are 15 kilometers apart. And what we can see is that the measurements are quite similar. So we can also visually inspect that if you have consistently low wind speed values, so below 0.5 meters per second, that could be malfunctioning of the anemometer or something that it was failed. In the example that you see, in this case, we have less than 1% of days with that kind of wind speed. So they are good observations. Here is an example for the relative humidity. When we see that measurements are above 100%, sometimes it's the sensor availability. So it has also more or less 5% error. So those observations should be corrected to 100%. But if the sensor consistently gives you higher measurements, then it's out of calibration. So you have to calibrate the sensor. Another thing that we also need to check is if the measurements were performed under reference site conditions. So it's not expected that a reference site condition has relative humidity lower than 5 to 10% in arid climates, or 30%. In the figure, you can see that this is a dry suburban climate, and we consistently see that the relative humidity is below. So this was not taken in a reference site. So we have to correct this kind of observations, or at least taking it into consideration when using it to compute reference evapotranspiration. So Dr. Allen did a study that it's available in the special issue, and he conditioned the observations when under desert conditions. And to do so, he compared and used reference site observations. This is the example for temperature, and you can see that maximum temperature is much above when it's measured in desert climate. So using the reference site condition, it was able to condition those values. This is another example of the same study with vapor pressure, and you can see that in desert conditions, it's much below. So it has to be conditioned, the observations. So the overall, the impacts can be of 20% reduction when you condition the measurements. So this is a very good example. And in this paper, you have the entire methodology that should be used for the corrections. I'm not going to use so because it's so Now passing to the Penman-Montis equation using reduced data sets, we have done is to overcome the gaps on observations that are a major constraint for the reference evapotranspiration computations. We did this study where we parameterized the PMT equation. So as we already spoke about, we need different kind of observations, and sometimes the actual vapor pressure is not observed, in this case, the dew point temperature. So to do so, we can use the different approaches. We can use the aridity index, and then we can see if the climate that we are observing is humid or other types of climate. In humid climates, the dew point temperature is predictor is the mean temperature and not the minimum temperature. So in these cases, we have to use the medium temperature. For other types of climate, then we use the minimum temperature, and then it is adjusted according to the climate type, using a value of 0 that ranges from 0 to 4 degrees to adjust the minimum temperature. Then for wind speed, it's very difficult to predict, but we can use a local or regional average value, or then the world average that is 2 meters per second. And then we have the solar radiation, shortwave radiation, that can be computed using the temperature difference using a radiation adjustment coefficient, this KRS. But this KRS, it depends on elevation, on closeness to water bodies, aridity of the site, and of wind speed. And it can ranges from 0.12 to 0.24. So how can we estimate this adjustment coefficient? So we did a study where we used 588 weather stations in the Mediterranean, and we select stations from hyper-arid to humid climates. We use several predictors to test the adjustment coefficient and use different combinations, and we reached the conclusion that the radiation adjustment coefficient is better predicted with the different temperature of the temperature difference, the relative humidity, and the wind speed. So we developed multiple linear regressions, as you see here. We used a global equation that can be used in every type of climate, and also derived specific focused climatic equations. So we have one for each kind of climate. So these equations were then validated using 222 weather stations locating in several countries all around the world. And here we have the results. We have it for the different types of climate. So if we locally calibrate the radiation adjustment coefficient, but for that we have to have observations, and it's a time-consuming activity. We have a very good adjustment of of reference evapotranspiration. When we use the global equation, so the equation that can be used in every type of climate, then we have an increase in error, of course, but we don't need to have observations to calibrate this adjustment coefficient. So this is an overcome. So, and then when we use the climate-focused equations to derive the radiation adjustment coefficients, then results improve. So we can use those equations to adjust. So the best thing that the PMT equation approach has is that we can use observations and use the estimators, the predictors, when we don't have a certain variable that is used for the reference evapotranspiration. So we can have the Penrose temperature equation approach used when we only have one missing variable, when we have two missing variables, or when we only have temperature. And we can see this example that is from humid to semi-arid, applied to humid to semi-arid climates. We have low root mean square errors. So we also, in the same study, we also developed similar approach for the use of the Hargreaves-Samani equation that is broadly used by many researchers. So in the Hargreaves-Samani equation, a similar radiation adjustment coefficient is also used. So we also derived the global equations and climate-focused ones. And here we have the results. So when Hargreaves-Samani developed the equation, the default value for the KRS was 0.17, and we see that the error of estimation of using this default value is quite high, could reach 1.05 millimeters per day. But when we use the global equation, we have an improvement of the results, and also when we have the climate-focused equations. So main conclusions of this study was that using the PMT approach is very adequate for all types of climate. Then when we use the predictor minimum temperature or mean temperature for dew point temperature is very good, namely for the dry climates. And when you use the mean local or regional wind speed, it's preferable than using, of course, the world average, particularly on climates marked by aridity. And relative to the computation of shortwave radiation, the developed equations are very good to be used when there is no observations. And then we have that the Hargreaves equation can also be used using the KRS estimation equations. So Dr. Allen provided another study on gridded weather data. So several kinds of data sets were used, and so prior to they were evaluated in terms of accuracy. And what was observed is that in many cases there has to have a bias correction of those kind of data. Two examples, one for 2015 and the other is for the entire data set. And what we see here that for the several data sets that reanalysis data sets that were used in some parts of the country, they outperformed, and in others they were not so good. So we have that there is a large spatial variability of the accuracy of the different reanalysis data sets. So we have to look for the best one to use in the different locations. In another study that we performed here in Portugal, we used a reanalysis data set from the European Center for Medium Range Weather Forecasts. And first of all, what we did is to analyze the quality of the weather, the different weather variables. You have here the minimum and maximum temperature, and we see that there is an underestimation tendency for the maximum temperature and an overestimation of the minimum temperature, with a high error in the minimum temperature. In terms of dew point temperature and solar radiation, we see that the the gridded data sets are quite good, particularly in terms of solar radiation. And then for wind speed, the wind speed has an overall difficulty to be used in terms of reanalysis, in terms of accuracy. So because it contributes less for the computation of reference evapotranspiration, then we may use this kind of information. Then we had a different scheme for the reanalysis. So the first, we for each weather station, we looked around the gridded points that were 100 kilometers apart, and then we had a correction of the maximum minimum temperature and dew point temperature with the elevation. So the reanalysis one, of course, and then we just considered a few of the gridded, because they have to be well correlated, otherwise they are not so interesting. And then we selected just the grid points that were more correlated with the observations. So when we look at the raw data of the reanalysis to compute the reference evapotranspiration using just the nearest grid point, we see that the root mean square area is quite high. So we had to have, so in 88% of the locations, the root mean square error was above 0.75 millimeters per day. So we had to have a bias correction for the reanalysis. And we studied two approaches. One that it's an additive bias correction using just the closest grid point, and another that it's a multiple regression using the selected grid points. And we looked at for as I was telling, the reanalysis using uncorrected bias tends to overestimate reference evapotranspiration, but when we use the bias correction, results much improved. So we have to look, not only use the grid data sets of reanalysis, we have to check if they are good enough to be used, and which kind of errors are we having when using it. So finally, in the special issue, we also talk about the use of satellite data. In this case, the shortwave radiation using Meteosat second generation, and the products that are the reference evapotranspiration products that they provide. So in this case, this reference evapotranspiration products don't have ground observations. So the application was performed to Portugal and to islands in Azores that are very cloudy and windy. And we also use, again, reanalysis data from the European Center. So the objective was to evaluate the use of the satellite shortwave radiation and the introduction of this in the Penman-Montes temperature-only equation, and also to assess if the product of reference evapotranspiration was also adequate. So we see here that for the shortwave radiation, when we see it for the satellite, it's very, very good. Not so good for the reanalysis data, but nevertheless, it's not such a very high errors of estimations. So here is when we introduce the shortwave radiation into the computation of reference crop evapotranspiration, and again we see that very good results are obtained. So this is a good product that can be used when we don't have ground observations of shortwave radiation. So the satellites are very, very good. And then we also assess the product of reference evapotranspiration. This product is based on the satellite radiation shortwave radiation measurements and on the reanalysis of using the temperature of reanalysis. So we see, sorry. So we see that they are not so good. You have quite high errors of estimation in some locations. And now we have the results when using the shortwave radiation introduced in the Penman-Montes temperature only. So we have observations of temperature, maximum, minimum, and we have the shortwave radiation from the satellite. Then we predict the dew point temperature from the temperature difference, and sorry, from the minimum temperature and mean temperature, and reduce the average local wind speed. So we see, comparing the product with the PMT, that we have much better results when using the PMT approach with the satellite shortwave radiation. So in terms of conclusions, we see that the graded shortwave radiation from the geostationary satellite is very accurate, despite having some uncertainties in hilly locations and the humid island locations. That the reanalysis, it's not so accurate in terms of shortwave radiation. And then the reference crop evapotranspirations using the shortwave radiation from satellite are very accurate. The product presents acceptable results for most locations, but less for the humid islands. And then the PMT approach with the satellite shortwave radiation, it's very accurate, and it's more accurate than the satellite product. Thank you very much.
Thank you very much, Paula. So now if you can stop sharing your screen, and then I can introduce our next speaker. Our next speaker is Dr. Ramón López-Urrea. Is currently a research scientist with Water Management Research Unit, Technical Institute of Agronomy for Albacete Province, Spain. His expertise includes irrigation water management, crop evapotranspiration determination and modeling, strategies of deficit irrigation, irrigation shadowing systems to detect water stress in plants, models for simulating growth and water balance of crops. He has been an associate editor for the Scientific Journal of Irrigation Science since July 2018. He will give us now a presentation about his work on the lysimeters. Dr. Ramón, the floor is yours, and I'll stop sharing now. Thank you.
Thank you, Dr. Ragab. I'm going to share my screen. It's fine?
Yeah, thank you.
Okay. First of all, I would like to thank the International Commission on Irrigation and Drainage for the invitation to participate in this webinar. It is much appreciated. My presentation is focused on providing the required information to obtain good quality, representative, and accurate ET measurements when using lysimeters, mainly weighing lysimeters and helicovariant systems, highlighting the most common mistakes to avoid and the requirements to transferability of crop efficient values to different environments. The content of my presentation is as follows. I'm going to talk about the factors affecting ET accuracy of lysimeters and pitfalls to avoid, requirements of helicovariant systems, required information to be provided in support of crop ET and crop efficient data, descriptive information for lysimeters and helicovariant systems, transferability of crop efficient values to different location and climate conditions, and I'm going to talk about an example of the use of lysimeters to measure canal AT and produce curve coefficients that has been included in the specialism. As you know, ET measurements for lysimeters are very sensitive to environment factors, but many of which are ignored in practice. Trying to avoid the common mistakes and problems when using lysimeters, we must take into account that ET accuracy depends on a variety of factors, such as soil conditions inside the lysimeters and outside the lysimeters must be the same. The lysimeter must be surrounded by the same vegetation that is growing in the lysimeter. We must avoid lysimeter measurements being affected by the so-called bloom effect, where the area of the lysimeter vegetation has exceeded the effective area of the lysimeter. A high exposure wind that must be avoided due to its thermal conditions and the adaptive effects. Regarding the requirements of ED covariance systems in order to obtain good quality data, we can say that we need to have a sufficient and quite large fetch to establish an equilibrium boundary layer deeper than the instrument height. We must have sufficient elevation of instruments above the canopy. We need accurate high frequency instrumentation and ability to recognize the occurrence of advention, correcting data for the balance closure. That issue is very, very important, and we must pay attention on that. Check data when wind direction changes and on when flows line change with turbulence and when advention occurs. About the required information to be provided in support of gravity and curve coefficient data, I'm going to show some factors, some information, and this information should be provided in any study reporting ET values and producing new or updated curve coefficients. Some of this information is we need to know the plant variety and density, days of critical growth stages, soil type, irrigation time and general irrigation frequency and duration of this irrigation, method for measuring irrigation input, reference ET method, and quality control and quality assessment procedures for ET measurements and for the weather data. More detailed information is provided by Allen et al. In 2011 and Pereira et al. In 2021. Now talking about the required descriptive information for lysimeter, some of the most important information we must know is the dimension of the tanks, both inner and outer tanks, gap between inner and outer tank material and thickness, pictures of the lysimeter with vegetation and without vegetation, pictures of the lysimeter with vegetation, including the surrounded area outside the lysimeter, crop yields for the lysimeter and for the surrounded field, a picture of the landscape surrounding the lysimeter, calibration checks and estimated precision and accuracy, and method of lysimeter subconstruction, monolithic versus reconstructed. Some more required information. It's important to know some comments and notes on any difference between lysimeter vegetation and that of the surrounding field, the plant density of the field and the plants inside the lysimeter. Also, we need to know the plant height inside and outside the lysimeter and the drainage process for lysimeter. About the required descriptive information for ED covariance systems, it's very important or extremely important to know the measurement frequency, the footprint analysis, the height of the sonic anemometer and hygrometer relative to ground and vegetation height, anemometer and hygrometer instrument separation distances and the orientation. Sometimes a good picture about that is much appreciated. And also the types of correction to the fixed measurements and the specific software used for corrections. Some more required descriptive information for medical variance is the fetch length, in the predominant wind directions and the direction thresholds for data filtering, the description of measurement of net radiation and soil heat flux for any balance, closure assessment, and a description of the closure error amount and the method of closure. Here in this slide, you can see a graph with an example of a linear regression between the sum of turbulent fluxes, I mean heat and latent heat fluxes, and the available energy, net radiation minus soil heat flux, in a study conducted in our research facility during 3 wind seasons in a young almond orchard. Similar results were obtained for the 3 seasons with a lack of closure around 20%. These results are in agreement with the imbalance values traditionally reported in a variety of croplands and climates. And in this study, we use the residual technique to correct this imbalance. Continue with the required descriptive information for elecovariance systems. It's important to know the brands and maintenance of procedures for net radiometers and for soil heat flux sensors. Also for the sonic anemometer and hygrometer, a description of the number of and placements of these sensors relative to the vegetation and individual plants. Also the height of the net radiometer sensor to the soil and vegetation height. For soil heat sensors, flux sensors, it's important to know the method for measuring soil water content and soil temperature for correcting the measurements. For vegetation, a description of fraction of ground cover and leaf area index, both measured or estimated, and also a description of the vegetation type, extent and soil water status upwind of the vegetation being monitored. Although Dr. Pereira talked in his presentation about the importance of the transferability, I would like to say that when we were working on the update of the special of the FAO56 method, we found thousands of papers that I published during the last 20 years, reporting on the use of single and basal crop coefficients for nearly all field and vegetable crop. But however, the objectives of these studies were quite diverse, resulting in contradictory approaches when aiming at the transferability of crop coefficient values to different environments. So we consider it's extremely important to take into account some requirements for transferability. For example, how the referencity is calculated, and it's important that it was calculated using the FAO56 permanent of the ASCE permanent equations, standard cultivation condition to avoid any biotic or abiotic stress, optimal plant density and or planting dates, sufficient size of experimental plots, consideration of possible occurrence of local and regional adaptation, single and basal crop coefficient should be adjusted to the FAO56 segmented crop coefficient curve, and the observed values of both single and basal crop coefficient must be adjusted to a standard temperate climate. I mean a minimum relative humidity of 45% and wind speed of 2 meters per second. Also, we can find further information provided by Pereira et al. In 2021. Finally, I'm going to show use of Weighing Lysimeter moving lysimeter for measurements of ET and to produce crop coefficient for sprinkler irrigated canola. This study is included in the special issue. The experiment or the study was conducted in our Lysimeter facility located in Albacete in the southeast of Spain. This slide shows an overview of the Lysimeter facility and the surrounding area. We have 3 lysimeters, one for annual cross, a reference lysimeter, and a vineyard lysimeter. Here is a cross section of our lysimeter, where the mass change is used to determine gravity. The plot is 100 by 100 meters with a sprinkler irrigation system, and the lysimeter is located in the center of the plot. The dimensions are 2.7 per 2.3 per 1.7. Resolution is 0.02 millimeters water depth, and we follow the quality control, quality assessment recommendations reported by Allen et al. In 2011. In this study, the weather station was located in 1.5 hectares reference surface that was located less than 100 meters from the canola lysimeter. Daily reference CT was calculated using the FAO56 temperament equation. Here in this slide, you can see the single coefficients curve obtained during the 2 growing seasons. We use this coefficient were calculated using the ratio of the lysimeter gravity measurements and the reference CT calculated using the FAO56 equation, and these coefficient values were adjusted to the segmented coefficient group. In this slide, you can see the dual coefficient, the evaporative coefficient was calculated using following the FAO56 methodology, and the K-sub-CB was estimated from lysimeter single coefficient minus calculated evaporative component. Also, in this case, the K-sub-CB values were adjusted to the segmented coefficient group. And here in this table, you can see a brief summary of the field observed and adjusted to standard climate coefficient values for irrigated canola. It's a summary of the results where you can see also the ancillary crop parameters, specifically the maximum root depth, maximum crop height, and maximum fraction of ground cover. And finally, I would like to you 2 messages to take home. You shouldn't trust all the AG data published, as we can see early. You should ask about the representative and the quality of this data. And the second message, an important message, is you should take into account this information provided in this presentation when using lysimeters or helicovariant systems, as well as for other methods for measuring or estimating ET. Thanks for your attention.
Thank you very much, Dr. Ramón. And we are now going to the last really presentation of the day. And I'll share, if you could stop sharing, Dr. Ramón. Yeah. And I'll share my screen now. So now our really last speaker of the day, Professor Nebo Jovanovic, is currently Associate Professor in the field of Water Resources Management at University of Western Cape, South Africa. He has over 20 years of experience in water sector, having conducted, led, and published research and crop and hydrological modeling, dry land salinity, food security, and drought impacts in smallholder irrigated farming systems, and applications of remote sensing in water management. He was editor-in-chief of Agricultural Water Management from 2011 to 2020. He will talk to us now about the impacts, advantages, and issues when adopting the updated approaches to FAO56. The floor is yours, Professor Jovanovic. Thank you.
Thank you, Chair. I will share my screen. And I will start the slideshow. Can you see my screen?
Yeah.
In slideshow format. Okay, so I wanted to thank first all the co-authors and contributors to the special issue on updating FAO56, and also the ICID for organizing this webinar. I will make some considerations, firstly on the importance of using the proper terminology in our line of work. Then the applications of FAO56 to crop water requirements. I'll discuss the one-step versus the two-step approach. Then applications of FAO56 to irrigation scheduling. I'll talk about water-saving strategies and new technologies and opportunities in the field, and some take-home messages in the end. So it is very well known that different disciplines make use of different terminology in water management. That's the case of hydrologists, agronomists, engineers, and so on. But yet it's very important to give a proper definition of the terms used, because that is fundamental for water accounting. In the first paper of the special issue, we compiled a list of symbols and a glossary of terms that are related to the special issue, and we try to use consistently then this list through all the papers, all the articles of the special issue. In the management of agricultural water, we generally operate at the field scale. So the water use, we define it as the volume of water that is pumped or diverted or conveyed to the crop field. Okay, and out of this volume of water that is distributed, only a portion is consumed. Okay, so we call that water consumption or consumptive water use. It can be beneficial if the water consumption occurs through transpiration, through plant transpiration, or non-beneficial if it is directly water that evaporates from the soil. The other portion of the water used is water that is lost from the viewpoint of the field scale. So it's water that bypasses the root zone and ends up in the water resource through deep percolation, or water that runs off the field, okay, over land flow or runoff. So it's water that can be recovered, so it's recoverable by downstream users, but it can also be a volume of water that cannot be recovered for other uses. So in order to reduce the water use, especially in areas that suffer from water shortages, it makes sense that we target the reduction of the water losses and the reduction of non-beneficial water consumption. The dual crop coefficient approach of the FAO56 makes provision for this, for distinguishing between beneficial and non-beneficial water consumption, because it separates the water that is consumed through plant transpiration and the water that is that directly evaporates from the soil. So if we multiply this term by the grass reference evapotranspiration, we get the crop water requirement. And if we add the water stress coefficient, we can calculate the actual evapotranspiration. And the actual evapotranspiration is fundamental in calculating water productivities. The biophysical crop water productivity, which is the ratio of crop yield divided by the actual evapotranspiration, or for farmers and practitioners, it is very relevant, the economic crop water productivity. Is the ratio between the profit, because most farmers are mainly interested in profits, divided by the total water use. Okay? That's an important indicator, because under certain conditions, applying mild or moderate water stress is beneficial to get better profits by improving the yield quality. The challenge that we have is that the crop coefficients are not really transferable from site to site, from field to field, because they depend on the crop variety, they depend on planting density, they depend very slightly on geographical location and climate, but definitely they depend on farm practices, the irrigation method, the crop management, the soil management, the microclimate, and so on. So how do we adjust then the crop coefficients to make them a bit more transferable from site to site? In one paper of the special issue, we discussed the one-step versus the two-step approach. The one-step approach makes use of the original Penman-Monteith equation, which is a solution of the surface energy balance for evapotranspiration. And one of the reasons why the original FAO56, the one published in 1998, one of the reasons that it recommended the Penman-Monteith equation as reference above other equations is that it includes these resistance terms, the aerodynamic and the surface vegetation resistance. And this makes it suitable, if we know the resistance terms, we could calculate directly the actual evapotranspiration. The problem is that it is difficult to measure these resistances, and there are many models that are available to estimate them, but it's difficult also to interpret the data and the results because they depend on weather conditions, on the age of the plants, on the variety management, and so on. So they are not very straightforward to quantify. So that's why the one-step approach is usually used in research. Okay. The two-step approach also makes use of the Penman-Monteith equation, but parameterized for a well-watered grass surface. Okay, and if we multiply the evapotranspiration from that reference grass surface by a crop coefficient, we get the crop water requirement, evapotranspiration of the crop. We can use either the general crop coefficient or the basal crop coefficient, which refers specifically to the transpiration portion of ET. This is a less mechanistic approach, and according to some opinions, it is empirical in nature, but it has some elements of sound physics. Okay, first of all, because it originates from the Penman-Monteith equation, and in a way, the resistances are implicitly expressed in the crop coefficients that characterize the vegetation. It is more intuitive to the practitioner, to the farmer, and the problem is that the transferability. Okay? And as we saw in previous talks, this is being addressed. There are many different methods that we can use to address this problem, to adjust the crop coefficients to local conditions. One of the methods that was presented is the one of Allen and Pereira that we call for short AMP methods, published in 2009. It uses the effective canopy cover of the index and the crop height to adjust the crop coefficients for local conditions. So you've seen the results of the validation of this method in previous talks. Now for applications in irrigation scheduling, we would usually couple the FAO56 method to a soil model that would typically be conceptualized as the classic water tank, where the soil is divided into different layers. And as the water infiltrates, the tank of the first soil layer is filled, and when it gets full, it cascades into the next layer, and so on. So this type of soil water model is intuitive. However, that's not how the system works in reality. So it's a rough simplification of our understanding of the system. The water redistribution is not physically based. So we can't calculate or simulate processes like capillary rise or the horizontal movement of water in the case of micro-irrigation. And also we use generally an allowable depletion level that is constant, and that in reality is not true. It's not always true. So the alternative is the use of more physically based soil water models that are based on the finite difference solution of Richard's equation for water flow. That's more mechanistic, more physically based, but it's models that are very intensive in data requirements. So they need hydraulic properties, they need root water uptake parameters. They are often coupled with the crop growth models, so they need additional parameters. So it's not very easy to parameterize and calibrate these models. These models are also imperfect because we generally use bulk hydraulic properties as inputs, so they fail to capture the microscale, the pore size distribution, and so on. So there is like an uncertainty also with these type of models. But because of the intensity of data required. These models are usually used also in research on crop and soil water. Okay, so there is no question that we are doing all these modeling work and estimation of crop water requirements and irrigation scheduling practice for the purpose of saving water and for the purpose of increasing productivity. Okay, one of the papers in the special issue provides a review of strategies, methods, and technologies to reduce non-beneficial consumptive water use on farms, considering the FAO56 method. Like many other papers that were published in journals, this paper also has an history. So the original objective was to review international literature to try and find out how much water can be truly saved. So based on experiments that were done and published in the literature, what are the expected figures of water saving that can be achieved in practice. In reviewing the literature, we actually found that to be a daunting task, okay? Because we found a lot of published experiments that were laid out in a way that where we couldn't make use of the data, simply because the experiments are laid out for different purposes. So they are often poorly designed with control treatments that are not appropriate, and sometimes it's difficult to interpret the terminology because different people use different terminology and inconsistent calculations as a result. So after advice from Prof Pereira, we changed a bit the objective of this paper. So we produced, in the end, some recommendations on how to adjust the crop coefficients, and as a result, the crop evapotranspiration and water productivity, if certain water-saving interventions are implemented under field conditions. So we came up with summary tables, okay, where we indicated various water-saving interventions or measures that can be applied to save water, and we categorized them into categories. Okay, the categories were the irrigation method, then those that refer to irrigation management and scheduling, crop management, remote sensing, plant conditioners, mulching, soil management and amendments and conditioners, and microclimate. So we gave in these tables the general trends, what can one expect in terms of adjusting or modifying the crop coefficients under the various interventions or strategies or tools that we use to apply in the field. So, for example, interventions that aim at surface irrigation, water saving in surface irrigation, they would mainly be aimed at reducing the soil evaporation component. So we could expect the coefficient for soil evaporation to go down, and as a result, the water productivity would go up. Another example, plant conditioners. In this case, the basal crop coefficients react in different ways. If we use antitranspirants, for example, we should decrease the basal crop coefficients. If we use plant growth regulators, the basal crop coefficient will increase. For some of the coefficients, we actually don't know what the general trend will be. So we need to do more research for certain water saving interventions. So this is just a summary table. The attendees can download the papers from the special issue, and they will find in one of the papers that there is a very detailed explanation and recommendation on how different water saving interventions can impact on the crop coefficients and how to adjust them. Okay, I want to mention about some new technologies, and with new technologies come new opportunities. When we talk about new technologies, top of the list is remote sensing. So the use of satellite and drone applications to map evapotranspiration, to map crop coefficients, crop water requirements, also agronomic requirements, fertilization requirements, for example. These type of applications are applicable to large scales. So we talk about large scale monitoring in space, about high resolution of data and high frequency of data. And as soon as we talk about large scale, high resolution, high frequency, that means a lot of terabytes of data. And one of the emerging fields of research in water management is big data analytics. And it's not only about remote sensing data. It's also about ground-based networks. It's about information from social media, like photos, audio visuals, even emails. And big data analytics is a method that processes heterogeneous sources of data. So because of the large volumes of data, we would generally rely on another emerging field in research, that's cloud computing, okay? And what we call Internet of Things. So in one of the papers of the special issue, we tried also to review publications that make use of electronic automation and combined with wireless plant and soil sensors for real-time irrigation, for farm management, ultimately for precision agriculture. Now, the good thing is that the FAO56 approach is in a way compatible with all these new technologies, because it is sufficiently simple and sufficiently accurate. It doesn't need to apply very complex algorithms that need to be validated and so on. So there is a compatibility in that sense with these new emerging technologies. But obviously there are challenges. Okay? So the first challenge is how to package the wealth of information that's available out there into information that is usable. Okay? So to do that, we would use something like some methods such as machine learning or artificial intelligence to develop decision support systems. Also for real-time operations, we need to have short-term weather forecasting. That's not always available and it's not always accurate. Also, new technologies imply devices, software applications, services, hardware, power supply, secure network access, security and access control. So all of that costs money. Okay, so we are still in a development stage So that's also a challenge, the accessibility of these resources to the farmers and practitioners. Okay, I'll conclude with some take-home messages, what came out from the work done in this special issue. If we look at water savings, usually true water savings that can be achieved compared to sound conventional practices are not large. So we're talking about 20% or less. So that's not a lot at field scale, but if we translate that to catchment scales, that's large volumes of water that can be made available to other users. We found a lot of published studies that talk about manifold water savings. And this type of work should be questioned because for plants to accumulate biomass, they need inputs. Water is an input. So it is impossible to cut the water supply and get the same yield. That's not how the system works. Yet we find this type of publications, this type of studies published in journals. So for that reason, we need to streamline data collection and focus on sound field experimentation. It is very common that water saving practices are combined. Okay? So we would use different water practices combined in the same field. And for that, we need optimization to balance the crop water productivities with economics and engineering infrastructure. We need more research on transferability of crop coefficients and also on uptake into practice. So how to transfer the crop coefficients not only from site to site, but also from research into practice. There are many tools and models out there that we can use for agricultural water management. And we have to recognize that some of these tools or models are appropriate for research and others are more appropriate for practical applications. They are all usable, but some of them are just more fit, for research purposes than others. And on the other hand, others are more fit for transfer into practice. And I would like to highlight some of the promising technologies that we came across. There's the use of plant and soil conditioners, remote sensing applications, obviously, and Internet of Things. And the final take-home message from my side is download the special issue, use it as a reference, and cite it. I shouldn't say that, but let's say cite it if it is fit to be cited. Thank you, Prof. Ragab.
Okay, thank you, Dr. Jovanovic. Thank you very much. So now we have really some questions from the participants. And let me see if I can share. Actually, I copied them for ease of use. And let us see what sort of questions we have. Can you see the screen?
Not yet.
Not yet.
No.
So share screen.
आगे
Let me close the.
Yes.
Okay, I'll just close the PowerPoint that's in the backside. Yeah, the first question here says that while recording moisture content in soil, where we need to place the moisture meter or tensiometers, is it closer to the root zone or anywhere in the field? Any taker?
Yeah, it's. I think it's a good question in the sense that there isn't a specific answer to it. What we found is that the placement of the soil water sensors depends on the irrigation method, and it depends on the crop. Okay, so yes, certainly the root zone is something that we should target. In field crops, we assume that the root zone is evenly distributed across the field. So the positioning would really be done in such a way to avoid micro obstacles or to avoid border effects and so on. It's a bit more difficult to answer for tree crops because they have this typical two-dimensional water balance and radiation balance system. So certainly you would, to cover the entire span, especially under micro irrigation, under irrigation that is localized, like drip irrigation or microjets, you would need to measure, certainly for research purposes, in at different distances in the interrow space across a section that goes perpendicular to the rows. That's for research purposes. Farmers usually target the wetted area because they are interested in in how much water is taken up by the root system. But for research purposes, it would be good to have sensors installed in both the wet and dry areas. But I want to make another consideration here. It's not so much about the type of crop and about the root zone and the type of sensors. It's about soil variability. So because soil sensors are point measurements, you'll find that the placement of the sensors is gonna, it can be a very, very difficult thing to do. And generally we would need replicated measurements to cover the soil variability. Soil properties change very much in space, in depth, and for research purposes, we would need at least a number of replications to be able to give reliable, to produce reliable measurements of soil water content.
Thank you. The second question is.
Okay, I may reply to the second question.
Yeah.
Second, third.
Yeah.
Okay.
Yeah. Carry on.
Okay. When we use the crop coefficients from FAO56, that are the same that the updates we reproduce in the special issue. So you can go to FAO56 and take the old, or you can go to the special issue and you take what happens after the 97 or 96 when we combine the information up to now, let's say last year, published by many researchers that provide good work. The question is, we use these for transfer. You observe, you can observe every day you want, but calibrate at 10 days interval using crop watt, you can also do, because crop watt is a very nice model that you can always use. But one thing that you are saying is that you don't worry about lysimeters, because lysimeters are, to be appropriate, they are extremely expensive and extremely demanding on management. So for the normal use of crop coefficients, it is enough to go to a table, look at the coefficients that are the standard coefficients, and do not use any value above these, and eventually reduce a little bit. You have the segmented curve, and you adjust to your conditions. It's very easy and very simple. Don't complicate things, please. This the doctor, I cannot read very well, Labsetvar put another question, that is, are lysimeters the kind of way to verify your field work? No. You just have to do a good field work. And most of information that we use worldwide come from field work, not from lysimeters. Lysimeters are exceptions, let's say. When you use field work, you just please use a model, a soil-water balance model. Because then you just know if you close the observations or the data or soil-water data or not when running the observations. One thing I would say is that don't start using a model or don't start to assess observations after the crop is already established. No, you have to start before planting and end at least at maturation, at harvesting. The full season has to be followed.
Okay. Yeah, there is. We jumped on one question.
Yeah.
That question was about the impact of aridity in arid and semi-arid areas. I think we jumped from that question.
Where you see this?
It was the second. Yeah, from Pavan. It's here. Pavan Kumar Reddy.
Okay.
Yeah.
What is the impact of aridity? Okay. The impact of aridity, let's say, I was speaking about the aridity of the station. And the aridity of the station makes that this station does not provide data adequate to compute the evapotranspiration. But there is another aridity, that is the aridity of the climate. and the aridity of the climate has to be, the variables have to be observed in good field whenever possible with a green grass, or eventually with a less, more difficult alfalfa. And these, if it is observed like that, the results on ETO are comprising, including the aridity of the effects of the aridity of the climate. So the fact that the climate is arid or humid does not change things. The only change is that in arid areas is much more difficult to keep a good green grass to make observations.
I assume Dr. Paula would like to comment on aridity and.
Yeah, Professor Pereira already answered very well the question. I suppose the mix was between the climate aridity and the observation of the reference sites. And we have to take into consideration that the reference sites have to have the green grass and they have to be well watered. Otherwise, they will impact the measurements that are being taken. That's the main issue here. And the same applies to that application that Dr. Allen performed in the desert. You know that they have impacts of the desert on the measurements, of course, and so they have to have some corrections.
Dr. Allen, would you like to comment further, or?
Well, I would just add that the Pima-Monteith equation is a physical equation, and it's expecting to be fed data measured at 2 meters above the surface that's in equilibrium with the surface. In other words, the temperature, the humidity, the wind speed are because of what is happening at the surface. So the Pima-Monteith takes that 2 meter measurement, extrapolates down to the surface to estimate how much evaporation. But if we take arid data that has high temperature, low humidity, and feed that to the Pima-Monteith, the equation says, my gosh, what a hostile, challenging environment. I'm evaporating like grass and still the humidity is only 15% above my head. And we are giving it an impossible condition that cannot exist in nature. So we should not expect to be able to feed arid data to the Pima-Monteith and expect it to tell us what the ET from grass would be if we have an extensive, well-watered grass surface that humidifies the air and cools it. That's the data that we need to feed into the equation.
Would the other speakers would like to comment, or we go to the next question?
Ragab, I have one comment to the first question about where to place a soil sensor.
Okay.
It depends on which of the two questions we are attempting to answer. One is, do we want to measure total water consumption? In that case, we need many sensors, as Dr. Jovanovic indicated, placed throughout the profile so we can measure and integrate all the depletion. But if our objective is to schedule irrigations, we can often get by with one sensor placed nearly anywhere in the root zone where there is a response. And then we use that sensor not to tell us soil moisture, but to be an indicator. And we learn by watching the plant when the reading on that gauge is at a point where the plant needs watering. It reaches the management allowable depletion. And we learn what reading gives us that index. So, and you know, we can use an infrared thermometer or something to measure crop water stress, but just one sensor, and we establish a line, and then we use that to indicate the scheduling. So it depends on what the application is.
Yeah, thank you. If there is no other comments from Ramon, I will go to the next question. But however, there was a question related to lysimeters. Maybe Dr. Ramon would comment on the lysimeter question of VJ Laboratoire.
Which one?
Yeah, it's VJ Laboratoire.
Okay.
In that question, if you would you like me to read it, or you can see it clearly?
It's a question about something that said Professor Pereira about the.
Yeah.
But in my opinion, Dr. Pereira said that many of the data published in the literature using lysimeters are wrong or are of bad quality, and only a 5% is true. I don't know if in this proportion, but in my presentation, I try to explain or to provide information to avoid the major mistakes when we see in the literature ET data and coefficient data. Of course, when the weighing lysimeters, when are well managed, are very good system or the best system to measure the water consumption. That's my opinion.
Thank you. The next question for Professor Pereira once again, and from Sylvester. He says, how many crop cycles are required for effective and efficient transferability usage in FAO56 computation?
Thank you. There are two approaches on this question. If you have a perennial crop or if you have an annual crop. If you have a perennial crop, you better follow several cycles when the crop is growing, and to consider the effects of pruning. So it is a little bit longer to have the full data, but if you use to inform the people about, in your publications, about the density of the crop, about the fraction of ground cover, about the age, about the way how pruning was done, what kind of training system you are using, and so on, you may require just a few years. If you want to have a follow-up complete, you need more years of observations. For the annual crops, you need, of course, at least 2 years. But you have to know the climate where you are working, because as you understand, if you are using something like the cumulative growth degree days, like Professor Allen was explaining, you have a vision for that particular year. But if, and then you rely, because these cumulative growth degree days are available from other sources, you can see if the variation of the climate after the base temperature is filled what happens with this variability? If the variability of the climate is large, of course, you cannot be sufficient with just 2 years. But most of cases, 2 years are required, not a single one.
Thank you.
There is another question for me that is about the transferability. No,
Yeah.
no, about the aqua crop. So I don't know. So aqua crop is a model that is not for computing evapotranspiration and crop water requirements. It computes it, but it is not designed for that, but is designed for knowing the transpiration of the crop and several other characteristics, predict the yield of the crop. And it is mostly used for annual crops, very rare for perennial crops.
Yeah, thank you.
Thank you.
Any more comments from other speakers? If not, I will go to the next question, which someone is asking, where are these updated equations available? I assume that's in the special issue.
Yes, in the special issue, yes.
Is that the simple answer? Yeah.
Yeah.
Okay, thank you very much.
And now they were estimated, of course.
Yeah, thank you. I think the last question listed was from Muhammad Aziz. What's the place of the use of data collected from sap flow and irrigation? He wonders if you have sap flow data, what to do with the sap flow data. I think that's my understanding.
Yeah, Prof. Ragab, if I may just answer also Sylvester about the question on crop cycles. The benchmark for a publication of a study in a high impact factor journal is to have at least 2 years of crop data to corroborate that the FAO56 computations are transferable. But then it also depends a lot on the nature of the 2 cycles. So preferably one would need to have a year that's particularly wet and a year that's particularly dry. So that would corroborate even better whether the crop coefficients are transferable or not. So comparing 2 years or 2 seasons that are in a way they represent some opposite extreme conditions. And regarding a sap flow is a very important method because it is the only method that can be used to estimate more or less directly crop transpiration. So it finds its place very strongly in estimating, in separating the 2 components of evapotranspiration, the transpiration and the evaporation directly from the soil. The challenge with sap flow is that there isn't really another method that we can compare the data with that is actually the only method that we can use for an estimate of crop transpiration, unless we use a lysimeter and we cover the soil surface, and the measurements of with the lysimeter would then give you the changes due to root water uptake. So SAP-Flow is really a very important method that should be applied in the context of these dual crop coefficients and separating the effects of the two components, the evaporation and the transpiration. But the question is, what do we compare it against? Because the SAP-Flow measurement on its own is not entirely a direct measurement. So we measure heat flux, okay, the dissipation of heat, that we know it's related to water flux. But there are some computations that need to be done in order to calculate the water flux from SAP-Flow measurements. So it's not an entirely direct measure of plant transpiration. And there isn't another method that we can compare it with. So we have to trust it as it is. There are also some corrections that are involved that one needs to apply, and that all of these are sources of potential errors in the measurement. So so on its own, it's a very important method. It's almost a must-have when in collecting research data for dual crop coefficients, but it has its own challenges in a way.
Yeah, can I just add something to that? My experience with my colleagues, we use SAP-Flow for trees, because trees, they have trunk and very easy to attach those sensors. But the other comment is that if we multiply the AT node by the KCB, that's the crop coefficient for transpiration, would that be comparable to the SAP-Flow?
I can give an opinion.
Yep. Happy to hear that.
If you have a good model, let's say we use the SIM-Dual KC model, that is a soil water balance model, we can make the calibration of the model and then the validation just using the SAP-Flow converted into transpiration. It works perfectly, and it is absolutely compatible, at least for the observations that we have, with the evapotranspiration and with the soil moisture changes. So the thing I say is that we need to use a model, maybe because I am very lazy, and instead of doing all the calculations, I prefer to develop a model, help people develop a model, and then use the model. And I don't have to compute anything, because the model computes. So that's an advice. Be lazy intelligently, and then you just solve a lot of problems in irrigation.
Thank you. So I hope, I hope the message was received by the lazy and active participants. Thank you, Professor Luis Pereira. I think that's really all the questions we have listed, unless the central office have something and someone raising hands or something, maybe the central office can say. Otherwise, I'll go to my last really slide to conclude. So I'll go to, in this case, I'll go to my last slide. And, so for participants that we were lucky really to have 5 distinguished speakers today, and it was really very a knowledge really enriching day. We all learned a lot about really the updates, and as you see, we have really 5 important updates, and these updates as listed here, and really that's something really you take on board for your work, forthcoming work, and for your research and applications. So I would like really to thank you all, participants and the speakers, and I would like really to invite you for the next ICID 24th Congress in October, first week of October 2022 in Adelaide, Australia, and follow the ICID other events also at the website. And once again, really, I'm really very grateful to all of you for coming really today and putting your experience and all the new information and technology available to all young and senior irrigation practitioners. I would like to thank you, and I will leave here the floor to the central office to say a few words to close the session. Thank you very much.
Thank you very much.
Thank you.
Ragab, thank you very much, the ICID. Thank you very much, the colleagues that were here making the presentation. It was a pleasure to see your faces.
Yes.
And thank you very much for the people that is assisting to our presentations. And we are ready to help whatever they require. They can find out easy our addresses and communicate with us. Thank you very much again.
Thank you.
Thank you.
So at the end, I thank all the speakers, Dr. Pereira, Dr. Ellen, Dr. Paula, Dr. Ramón, and Dr. Nebo for their excellent presentations and very deep insights into a very crucial question of water requirement of crops and the efficiency in the water management. We are very happy to have a very large set of participants. We had about 500 participants, and we feel that they have all benefited a great lot. There were a few other questions also, which we will be collecting and passing it on to our presenters. And if they find it convenient to answer whatever those answers, we'll put it on our website along with the videos of the presentations, so that the people can satisfy their queries. And at the end, I thank all for persevering with us for a longer time than estimated, but it was a very rich and a very powerful experience for all of us. And I once again thank all the faculty and the participants. Thank you very much. And I also thank Professor Ragab for very efficiently and very competently handling the such an important webinar. And his support is very valued for us. Thank you.
Thank you.
So close.
Thank you. Thank you, everybody. Thank you, everybody.
Thank you. Thank you. Bye-bye.
Bye-bye.
Fantastic.
Thank you.
Bye-bye.
Bye-bye. Bye-bye. Thank you.